The grounding electrode conductor on a separately derived system originates at the grounding electrode itself. From there, it connects to one of several points. Firstly, the X0 lug of the transformer if one is present. Secondly, the equipment grounding terminal bar, again if one is used. Thirdly, a ground bus, should that be the system's configuration. The crucial aspect is that the grounding electrode conductor must maintain continuity from the grounding electrode to whichever of those points it connects to. Splices in the grounding electrode conductor are only permitted if they are reversible. Let's consider an installation that incorporates a ground bus. In such a setup, the grounding electrode conductor runs continuously from the grounding electrode to the ground bus. There might be a break in the conductor's path between the ground bus and the X0 lug. However, provided that the connection at the ground bus is irreversible, typically achieved with a set screw type lug, this arrangement aligns with code requirements. So, to reiterate, the described installation is deemed acceptable under these conditions. Firstly, the grounding electrode conductor is continuous from the grounding electrode to its connection point at the ground bus. Secondly, the break in the grounding electrode conductor at the ground bus is irreversible, presupposing the use of set screw type lugs or an equivalent reversible connection method. It is important to determine what an irreversible connection means. An irreversible connection means you cannot undo the connection without destroying the lug, connector or conductor. A compression connector using the proper tool is deemed irreversible. A wire nut is not irreversible. A split bolt is not irreversible. A set screw connector can be considered irreversible if properly torqued and installed. Keep in mind the correct tool and die are used in making a compression connection, and the tool has been calibrated according to manufacturer's recommendations. It is paramount to select an appropriately sized grounding electrode conductor. The sizing should be based on factors such as the grounding electrode type and the fault current rating of the grounding electrode system. Always consult the applicable electrical code for the specific and detailed requirements related to conductor sizing and grounding practices. Let's talk about what the X0 lug is. On a separately derived system, such as a transformer or generator, the X0 lug is the designated terminal for connecting the neutral conductor to the transformer or generator. This point serves as the reference point for the system's voltage and is typically grounded, providing a path for fault current to return to the source. The X0 lug is crucial for maintaining a stable and safe electrical system, ensuring proper voltage levels and minimizing the risk of electrical shock. Let's elaborate on the equipment grounding terminal bar. The equipment grounding terminal bar, often found in electrical panels or enclosures, serves as the central connection point for all equipment grounding conductors within a system. Its primary function is to provide a low impedance path for fault current to return to the source, facilitating the quick operation of overcurrent protection devices like circuit breakers or fuses, thereby minimizing the risk of electrical shock and equipment damage. All non-current carrying metallic parts of electrical equipment must be bonded to this bar to ensure electrical safety. Now let's consider the function of the ground bus. A ground bus, similar to the equipment grounding terminal bar, is a conductive bar used to connect multiple grounding conductors together, providing a common grounding point for electrical systems or equipment. It serves as a central hub for grounding connections, ensuring that all grounded components are at the same electrical potential, minimizing the risk of ground loops and electrical noise. The ground bus is essential for maintaining a stable and safe electrical system, particularly in sensitive electronic environments. When we talk about a continuous grounding electrode conductor, we mean that the conductor should run uninterrupted from the grounding electrode to the designated connection point, whether that be the X0 lug, equipment grounding terminal bar, or the ground bus. Any splices or connections in the grounding electrode conductor can introduce impedance and reduce the effectiveness of the grounding system, compromising its ability to safely carry fault current. Therefore, the electrical code mandates that the grounding electrode conductor be continuous except for reversible connections to ensure a reliable and low impedance grounding path. Let's dive into what constitutes an irreversible splice. An irreversible splice is a connection between two or more conductors that is made using a method that permanently joins the conductors together such that they cannot be easily separated without damaging the conductors or the connection. Examples of irreversible splices include compression connectors installed with the appropriate tool and die, exothermic welds, and certain types of crimp connectors. These types of splices provide a reliable and low-resistance connection that is essential for maintaining the integrity of the grounding system. Let's talk more about the grounding electrode. A grounding electrode is a conductive rod, plate, or other object that is buried in the earth and used to establish a direct connection to ground. Its purpose is to provide a low-impedance path for fault current to dissipate into the earth, minimizing the risk of electrical shock and equipment damage. Common types of grounding electrodes include ground rods, metal water pipes, and concrete encased electrodes. The selection and installation of grounding electrodes must comply with the requirements of the applicable electrical code to ensure effective grounding. Now let's talk about what we mean by separately derived system. A separately derived system is an electrical power source such as a transformer, generator, or solar inverter that is not electrically connected to the primary power source. Separately derived systems are used to provide isolation and voltage transformation, allowing for the creation of electrical systems with different voltage levels or grounding configurations. Because they are not directly connected to the primary power source, separately derived systems require their own grounding electrode system to ensure electrical safety. We must also touch on fault current. Fault current is the excessive current that flows through an electrical circuit during a fault condition such as a short circuit or ground fault. Fault current can be very high, potentially causing damage to equipment and posing a risk of electrical shock. A properly designed grounding system provides a low impedance path for fault current to return to the source, allowing overcurrent protection devices to quickly interrupt the circuit and minimize the duration of the fault. The grounding electrode conductor plays a crucial role in carrying fault current back to the source, ensuring that the overcurrent protection devices operate effectively. Sizing the grounding electrode conductor for a separately derived system involves several steps to ensure it can safely handle fault currents and effectively ground the system. Firstly, identify the size of the largest ungrounded conductor of the separately derived system. This conductor will determine the minimum size of the grounding electrode conductor. Secondly, refer to the National Electrical Code Table 250.66, which provides guidance on the size of the grounding electrode conductor based on the size of the largest ungrounded conductor. This table helps you determine the minimum size required for the grounding electrode conductor. Thirdly, consider the material of the grounding electrode conductor, which can be copper, aluminum, or copper-clad aluminum. Ensure that the conductor material is compatible with the grounding electrode and other components of the grounding system to prevent corrosion and ensure a reliable connection. Fourthly, select the appropriate grounding electrode. Common grounding electrodes include ground rods, metal water pipes, and concrete encased electrodes. The type of grounding electrode will influence the overall effectiveness of the grounding system. Fifthly, ensure that the grounding electrode conductor is properly connected to the grounding electrode in the separately derived system. The connection should be made using approved connectors and methods to ensure a low impedance connection. Sixthly, verify that the grounding electrode conductor is protected from physical damage. This may involve running the conductor through conduit or other protective measures. Seventhly, inspect the installation to ensure that all connections are tight, secure, and free from corrosion. Regularly inspect the grounding system to maintain its integrity and effectiveness. Eighthly, consider the requirements of local codes and regulations. Local codes may have additional requirements for grounding systems, so it's essential to comply with all applicable regulations. Ninthly, document the grounding system design and installation, including the size of the grounding electrode conductor, the type of grounding electrode, and the location of connections. This documentation will be helpful for future maintenance and troubleshooting. Tenthly, test the grounding system to verify its effectiveness. This can be done using a ground resistance tester to measure the impedance of the grounding system. If the impedance is too high, adjustments may be needed to improve the grounding system. Always consult with a qualified electrician or electrical engineer to ensure that the grounding system is properly designed and installed. A properly designed and installed grounding system is essential for protecting people and equipment from electrical hazards. The National Electrical Code provides comprehensive guidelines for grounding electrical systems, including separately derived systems. Following these guidelines will help ensure a safe and reliable electrical system. When dealing with separately derived systems, it is important to understand that the impedance is lower when the grounding electrode conductor is connected to the X0 of the transformer. This will create a corner-grounded system. If you connect the grounding electrode conductor to the ground bus instead of the X0 terminal, this will be a high-impedance ground, which is less effective at clearing ground faults. Keep in mind when installing ground rods that one ground rod is not sufficient. You must install 2 or more ground rods which are at least 6 feet apart to reduce impedance to ground. This ensures proper current flow to trip the breaker.